So we ended the last class talking about additivity of defects, right? You take one triangle, chop it into two triangles. The defect of the larger triangle is the sum of the defects of the two pieces you cut it into. We're gonna come back to that, but we're gonna take a small detour for a second and consider the following. So consider triangles ABC and triangle DEF, so that angle A is congruent to angle D, angle B is congruent to, angle E, and angle C is congruent to angle F. Alright, so I have two triangles where all of the angles are congruent with each other, right? Here's ABC, and here's angle or triangle DEF. Let me not draw them so they look Euclideanly congruent. Let's go with this one, it's much smaller. So let's assume no two corresponding sides are the same length, right? So assume no two corresponding sides. What would happen if a pair of sides did have the same length? Say, for example, suppose DF and AC are congruent.
They all would.
Say that again?
They all would.
Yeah, right, because I could invoke ASA at that point, ASA, and they'd be congruent. So this is why I'm saying is suppose not, otherwise the triangles are congruent by ASA. Alright, so we know in Euclidean geometry this is possible. We have a name for this. These are not congruent triangles, but they are similar triangles, right? In fact, it's a definition of similar is the same angles everywhere. So in Euclidean geometry, triangle ABC and triangle DEF are not congruent, but they are similar. So in hyperbolic geometry, what happens here? And we're going to show that this is impossible. In hyperbolic geometry, it's not possible to have all three angles the same, and yet no sides are the same length. All right, so I just put a question mark for now, but we're going to show that this is simply not possible. So, okay, no two corresponding sides are the same length. So let's assume, without loss of generality, assume, let's say AB and AC are longer than these two corresponding sides here. So assume AB is bigger than DE, and AC is bigger than DF. Why am I allowed to do this? Why is this sort of without loss of generality? Well, it must be the case that one triangle has two sides longer than the other one, right? If it only has one side or zero sides longer than the other one, then the other triangle has two sides longer than the other one, right? So I know one of these triangles has at least two sides longer than the other, and I'm saying without loss of generality, just assume it's the first one and let it be these two sides, right? If it's not, relabel everything so it is. So this really is without loss of generality. And now we're going to do our standard stuff. AB is longer than DE, so we'll come in here and we'll just choose a point E prime so that AE prime is the same length. So let E prime be such that A, E prime, and B are collinear with E prime in the middle. And the length of AE prime is the same as the length of DE. And we'll let F prime be such that A F prime then C, and so that A F prime is equal to DF. Okay, so I've built this triangle inside of ABC. That is, in fact, obviously congruent to DEF, right? By SAS, AE prime, F prime is the same triangle as DEF, right? Or congruent to it anyway. So by SAS, triangle AE prime, F prime is congruent to triangle DEF. That, of course, means they have the same angle sum. So the angle sum of triangle A, E prime, F prime is the same as the angle sum of triangle DEF. And if they have the same angle sum, they must have the same defect, right? Because the defect is just 180 minus the angle sum. So the defect of triangle A, E prime, F prime is the same as the defect of triangle DEF. But how do those relate to the angle sum of the original triangle ABC? Well, ABC has the exact same angles as DEF, right? So the angle sum of DEF is the exact same as the angle sum of ABC, which is the same as the defect. which means they have the same defect as well. So now from last class, I want to invoke what we were doing last time. What do I have here? Think of this as a triangle that's cut into by this intersecting line. I've got this triangle that's cut into a triangle and a quadrilateral. And we proved last time that the defect of the whole thing would be the sum of the defects of both of these, right? So from last class, the defect of triangle ABC is the defect of triangle A, E prime, F prime, plus the defect of this quadrilateral. I don't think the textbook tends to put a little quadrilateral symbol here. When they're dealing with quadrilaterals, they just put all 4 letters, but I like the little square in the box. We'll call it E prime, B, C, F prime. What does that imply? Moreover, what can I say about this?
It's greater than 0. It has to be, doesn't it?
So to not have a contradiction, it would have to be, yeah. So there's going to be our contradiction. I already have that this is equal to this. So if I'm going to claim now that this is equal to this plus something else, then this piece has to be 0, right? So this implies, combined with this line above it, that the defect of this quadrilateral is 0. Which is a contradiction in hyperbolic geometry. Which is a contradiction in hyperbolic geometry. Every polygon in hyperbolic geometry has a non-zero defect. Otherwise, you're in Euclidean. So therefore, how do we get this contradiction? We assume that we didn't have a single pair of sides that were congruent, right? So the result is that we must have a pair of sides that are congruent, and therefore these two triangles must have been congruent to start with, right? By SAS. So this implies, therefore, there must be a pair of congruent sides, and that implies that the two triangles ABC and DEF are congruent. So in hyperbolic geometry, there is no such thing as being just similar but not congruent. This says if you are similar, then you must be congruent, right? And I'm going to say this is a theorem. I can make this very wordy, but we all know what we're saying here. So we'll just say AAA is a triangle congruence condition. It's a triangle congruence condition hyperbolic geometry. In Euclidean geometry, it only tells you they're similar, but in hyperbolic geometry, we have this beautiful result. In the next section, we'll get to area. We'll talk about area. We'll talk about how you define area of triangles and shapes and whatnot. But if we have a reasonable definition for area, which we will, then what is this really saying? This is saying that, what does it mean for triangles to be congruent? It means they have the same size and shape, right? So same size and shape, literally the same thing, just moved around the plane by some rigid motion. So congruent triangles have the same area. You'd expect that, right? If we have a reasonable definition for area, congruent triangles have the same area. Well, this says that triangles are really determined by just their angle sum. If you know their angle sum, if you know the sum of the angles, then you know their area. So that's kind of cool, right? And in Euclidean geometry, that's not nearly enough, but this says that somehow if you just know the angles of the triangle, then you know exactly what the area is. So we'll come back to that when we talk about area next time. But moving on, I just want to state a full generalization of what we were doing in the last class. So this is just a generalization of last class. Which is last time we had this result, you take a triangle, you cut it into two triangles. The defect of the original is the sum of the defects of this guy. Then you can slice it again, right? Slice into three triangles, the defect is the sum of all three. We'll just generalize this for all polygons, so, or at least convex ones. If a convex polygon is partitioned into triangles, in any manner, the defect of the polygon is equal to the sum of the defects of the component triangles. So just a full generalization from last time. This isn't true for just triangles or quadrilaterals or anything. You take any convex polygon that you want. Here's here's a nice convex pentagon. Slices up into triangles again any way that you want. Is that a triangle? This is a triangle. Slice it into triangles any old way that you want. And the defect of the original polygon will be the sum of the defects of all of these triangles. And if you're thinking in terms of area, you wouldn't be surprised if I told you this result about area, right? If I said the area of this polygon is the sum of the areas of all these things, well, that wouldn't be surprising at all. That's, of course, just what you'd expect. And now we know somehow that angle sums, defects have something to do with area. So this is really sort of saying the same thing. It's that if you want the defect of the whole thing, just add up the defects of all of these. By the way, what is the defect of a polygon? Let's make a note. Defect of an n-gon angle sum of the Euclidean angle sum of a three-gon, a triangle, is what? 180, right? Angle sum of a Euclidean four-gon, a quadrilateral, is 360. So for an n-gon, the Euclidean angle sum is n times, what is it? 180 times 4 minus n. No. N minus 2. There we go. 180 times n minus 2 minus the actual angle sum. So for a five-gon, it's 540 minus the angle sum and so on. Any questions so far? All right. So we'll move on, and this will sort of be the wrapping up the chapter here. Is this concept of equivalent polygons. So we're going to start off with this question of when do two polygons have the same defect? All right, so that's a question. When do two polygons have the same defect? Here's one obvious answer, if they're congruent. Obviously, if they're congruent, they're literally the same, just moved around the plane. Of course, they have the same defect. Congruence implies they have all the same angles, interior angles, so again, of course they have the same defect. But can I weaken that, right? Is it possible for two polygons to not be congruent and still have the same defect? The answer is, I think, quite obviously yes. So we're going to delve into this. But first, let's consider the following. Consider the following. So we'll take a triangle. Let triangle ABC be a triangle. Again, a little bit redundant, but let this be a triangle. And let M and N be the midpoints of sides AC and BC, respectively. So I'll draw a picture here in a second, but let me just continue on with what we're doing. So let's drop perpendiculars. Drop perpendiculars from A, B, and C to the feet overall at P, Q, and R, respectively, on the bi-infinite line MN. All right, so what do we have? We've got I'm only drawing one case here. This is sort of the acute triangle case, but that's okay. We've got ABC, we're going to look at the midpoints of AC and BC. I've called them M and N. I'll just draw a line and hope it intersects around the midpoint. So there's M, there's N. And we're coming into each of these three points, A, B, and C, and we're dropping perpendiculars to the line to P, Q, and R. So here we have P, there's a right angle, Q, these are right angles, and R. Again, we know we can do this. We proved this at one point that on a line there's always a point that I guess we proved the other way that you can sort of erect a perpendicular from passing through a given point. And what do we have so far? We have AM is the same length as MC because those are midpoints, and BN is the same as CN. Okay. All right, so I'm going to make a couple of claims. Claim number one. I have, my first claim is that ABRP, actually I think in my notes I go the other way around. I don't know why I've done this in my notes. Traditionally, mathematicians sort of label things and count things counterclockwise, but I'm going to call this the security quadrilateral APRB. My claim is that this is a security quadrilateral. I've got two right angles here. All I have to do is show that these sides are the same length, AP and BR. All right, so claim number one is that APRB is a security quadrilateral. And I'm just gonna start calling these SQ. All right, so just for short. Claim is that it's a security quadrilateral. How do I do that? Well, there's two more angles in here that I haven't. I guess two more congruences that I haven't labeled. These are vertical angles, right? Those are vertical angles, so those are congruent. And these are vertical angles, so those are congruent. So really quick proof using congruences and transitivity and so on. This triangle MPA, my claim is that it's congruent to triangle MQC. Again, by a congruence condition we don't often invoke, but I have to invoke it here. I've got AAS. So yeah, so these are congruent by AAS. Yeah, and same thing over here. I've got congruence between these two triangles. So triangle NRB is congruent to triangle NQC. Once again, by AAS. So just symmetric picture on the other side. So what did I want to do? I wanted to show that AP and BR are the same length. Well, I have that AP now, let's see, 1, 2, 3 I think I can go with. AP by congruence of triangles, AP is the same length as CQ. And by congruence of triangles, these two, CQ is the same length as VR, which is what I wanted. All right, so these two results together give me that AP, we'll go with lengths. AP is equal to CQ, which is equal to VR. So I do indeed have a security quadrilateral built in this picture. With base, the base is the opposite way around. Base is actually at the top here in this picture. It's PR. All right, so that implies the result that APRB is a security quadrilateral. And I'll just make a note with base PR. Erases. I don't need to. All right, so here's my second claim. Claim number 2. My claim is that this original triangle ABC and the security quadrilateral we built, my claim is they have the same defect. All right, so the defect of triangle ABC is the same as the defect of the security quadrilateral. Not hard to do, you just have to go through the angle sums. So let's make a note about congruences really quickly. And let me just label some angles here. So I'll call this angle 1, I'll call this angle 2, I'll call this angle 3, 4, 5, and 6. All right, so I've labeled 6 angles. And note by the congruences we just established, I have that some of these angles are equal to each other. Angle 1 is congruent to angle 6. Is that right? I suppose it is, but actually not necessarily. It's angle 1 is congruent to angle 3, sorry. Note, angle 1 is congruent to angle 3. And angle 6 is congruent to angle 4. That's what we established with our triangle congruences. And we'll just write down the defects of those triangles, and we'll show that using these congruences are actually the same. So not much to do here. The defect of triangle ABC is going to be 180 minus its actual angle sum. So angle 2 plus 5 plus, let's go clockwise. 2, 3, 4, 5. Minus the measure of angle 2, minus the measure of angle 3, minus the measure of angle 4, minus the measure of angle 5. Let's substitute. Let's replace with these other angles. This will be 180 minus, what do we have? Measure of angle 3 is measure of angle 1, so we'll substitute there. Minus measure of angle 1. Measure of angle 4 is measure of angle 6, so we'll substitute there. And I'll skip a line. Usually you compute both of these separately and then show they're equal to each other, and then maybe string it together like this in a nice string of equalities. We're going to do it all in one go. In my last line, I'm going to claim that this is the defect of the security quadrilateral. So we'll work backwards. In this line, let's just think about what the defect of the security quadrilateral is, and I promise you it'll be equal to this line above it. So what is the defect of the security quadrilateral? Well, it's a quadrilateral, so it should be 360 minus its angle sum. And what's its angle sum? Well, it's 300. Its angle sum would be 90 plus 90, so 360 minus 90 minus 90 for those two right angles. And then I've got angle 1 and 2, so minus measure of angle 1 minus measure of angle 2. And then I've got angles 5 and 6. Minus measure of angle 5 minus measure of angle 6. All right, so I sort of worked backwards here. We just to stop right here. We computed the defect of ABC, we got this thing. We computed the defect of the security quadrilateral, we got this thing. But these are, in fact, equal, right? So we're done. There's the claim. So why is this nice? Well, we know a lot about security quadrilaterals, right? We know a lot. They pop up all the time. They're really nice to use. And this sort of says that given any triangle, I now have this method for constructing a security quadrilateral that has the same defect. We call this the associated security quadrilateral, but we're going to make one more observation before we do that. And I'm running out of time here. We'll see what we can do in 5 minutes. So one more observation. We can view the security quadrilateral APRB as consisting or being made up of the three component parts, consisting of three components. What do I have in this picture? I've got three triangles. Three component parts for the security quadrilateral. Triangle MAP, triangle NBR, and this quadrilateral piece here, right? Of the three components, triangle MAP, triangle NBR, and quadrilateral AMNB. Okay, so and we can view the original triangle ABC as consisting of the three parts. What about triangle ABC? Well, here I've got, I can think of this as being part MCQ, triangle MCQ, triangle NCQ, and quadrilateral, once again, AM and B. All right, so I'm just saying here, I can think of the security quadrilateral as being this triangle plus this quadrilateral. And the original triangle being this triangle plus this quadrilateral. But remember, this is congruent to this, and this guy is congruent to this guy. So up to congruence, these two shapes, the triangle and the quadrilateral, are really made of the same pieces, right? They're both made of this thing, and they're both made of these two triangles. Up to congruence, right? Not literally the same triangle, but congruent triangles. So, but triangle MAP is congruent to triangle MCQ, and triangle NBR is congruent to triangle NQC. So they really consist of the same parts. And by same, I mean up to congruence. But I think you're probably getting to the point in your math career where you're used to thinking of congruent things as being the same. So in a very strong sense, in fact, this is exactly why they have the same defect. They have the same defect because they're made of the same parts. Our definition for something called equivalence of polygons that we'll do next time doesn't involve quadrilaterals. It involves just slicing into congruent triangles. But I can do that here, right? We had this piece, this quadrilateral, was common to both of them. Just slice it into two triangles. And now they're all made up of the same sort of congruent triangles. And so further, we could slice quadrilateral A, M, and B along a diagonal into two triangles to observe that triangle ABC and its associated secured quadrilateral APRB is, or are, let's say consist, let's say are made up of, just of the same congruent triangles. And so that's what we'll pick up next time. We'll talk about equivalency of polygons, but two polygons are equivalent if you can slice them up into a bunch of congruent triangles. I promised I would say a few words about the homework. Let me see. It's from 6.3, right? Need to find it. Is it from 6.4? No, that's from 6.3. That's why none of them look familiar. I think I assigned number 5, explain why lines with a common perpendicular cannot have a second common perpendicular. Just assume they do. Draw a picture, you'll see something goes wrong immediately. It's a one-liner. That one's not hard. Number 7 I also assigned. This one, I guess I can point you in the right direction on. So this is number 7. It says, prove that if two lines share a common perpendicular, so here's two lines. Suppose they share a common perpendicular, so there we go. It says, prove that the distance between the lines is the least on that segment. Well, how do you measure distances between lines? You take a point, and you take a point and you draw up a perpendicular and you measure the length of that line segment. So my claim is that this is the least distance between these lines. Well, okay. Suppose I take another point. Let's call this A, B, C, and D. Suppose I took another point and suppose I dropped a perpendicular from C to D. Right, what do you want to do? You want to show that AB must be strictly less than CD. Do you agree? I mean, how do I measure the distance from this point to this line? Well, I drop a perpendicular. All right, so the distance between the lines at this point is the length of this perpendicular. And you want to show that, that no matter what point you choose, no matter which line segment you look at, this is always longer than this one, right? Well, it's stated somewhere as a theorem in the book, but we actually proved it Wednesday's class last week, right before the exam. As a review, we proved this for neutral geometry, right? For Lambert quadrilaterals. This is a Lambert quadrilateral, and we proved that in Lambert quadrilaterals, the side between the two right angles is less than or equal to in length the opposite side. So all you have to do, invoke this theorem, we've proved it, you don't have to reprove it, that's fine. Invoke that, and then just show that in hyperbolic geometry, because we're no longer neutral, shows in hyperbolic geometry you can't have equality. And so just rule out the equals case. And the other hardest one, 9 was just the opposite direction thing we did in class. You should have no trouble with that. It's triangle congruent stuff. Is number 12. It asks, okay, rectangles don't exist in hyperbolic geometry, but do rhombuses. A rhombus is just a quadrilateral with four sides of equal length. The answer is yes, so that at least will have you halfway there. It's yes, you don't have to keep looking for ways to prove they don't. And the way you would do this is, I'll just give you a big hint here, just take any old line segment. Take any old line segment and work with the perpendicular bisector. All right, so take the midpoint X and construct, by the rate construction postulate, SMSG number 12, construct a perpendicular bisector. Right, huge result here. We're actually doing a neutral result. We're showing that neutral geometry rhombuses exist, therefore they exist in hyperbolic geometry. But what's true about points on the perpendicular bisector? With respect to A and B? They're equidistant, right? So if you choose, take any point here, I know those are the same length. If you choose appropriate points, you should be able to construct a foregone, a quadrilateral, where all the sides are the same length. So this picture pretty much does it all for you, but I'll leave the last couple of details to you.